Well, hello and welcome back. Today I believe we are notes number 12 and the topic is matrices. And I'm excited to talk to you guys about matrices. This is a new topic for a lot of students. Most students haven't worked with matrices before. Maybe you don't know what they are. So it's kind of exciting and fun to get to learn something totally new. The singular is matrix, the plural matrices. And what we're going to do today is learn some of the basics, like what is a matrix and how do you operate on it. And then over the course of the next few days, we'll learn how we can solve systems of equations with matrices. And there are also various geometric applications. All kinds of applications, really, for matrices. We just get to look at a few. So a matrix is really simply a rectangular arrangement of numbers, and we call the numbers elements. So here's an example. When we name a matrix, we typically use a capital letter. So this is matrix A, and we put square brackets around the rectangular arrangement of numbers. So you can see that inside the square brackets, I have 3 rows of numbers, 2 columns of numbers. So when we read the numbers, we just read across. We would say 2, 7, -1, 0, 5, 2. We also talk about the size of the matrix. We refer to that as the dimensions of the matrix, and the dimensions is always denoted by the number of rows by the number of columns. So rows first, columns second. So in my example, matrix A, how many rows does it have? Rows go across. So it has 3 rows. And how many columns does it have? Columns go down, so it has 2 columns. So we would say that matrix A is a 3 by 2 matrix. Okay, now we're going to move on to matrix operations. So we're going to look at addition, subtraction, multiplication by a scalar, and matrix multiplication. We don't really have matrix division. Instead, we have a concept called multiplying by an inverse. So we'll get to that later. Okay, so here we have 2 matrices and we're going to add them. First of all, you can only add them if they have the same dimensions. You can only subtract them if they have the same dimensions. So notice that both of these matrices in number 1 are 2 by 2. 2 rows, 2 columns. So the way we're going to add them is to add the elements in like position. 0 plus -1 is -1. -4 plus 8 is 4. -1 plus 0 is -1, and 5 plus -3 is 2. So there's our answer. In number 2, we're subtracting. And once again, we need to check to make sure that the dimensions are the same for both matrices, and they are. And the dimensions of the resulting matrix will also be 3 by 2, so you can set it up ahead if you want. And then we'll just subtract numbers in like position. 4 minus 2 is 2, 6 minus 3 is 3, -2 minus -4 is 2, 2 minus 2 is 0, 1 minus 3 is -2, and 5 minus 1 is 4. Okay. How about number 3? We're adding these matrices, but let's check to see if they have the same dimensions. The first matrix has 2 rows and 2 columns, and the second matrix has 3 rows and 2 columns. The dimensions are different, so it is not possible to add these. We just don't have the numbers lining up. Okay, multiplication by a scalar means multiplying a matrix by a number. The scalar is the non-matrix number. Like in this problem, 4 is a scalar. This is really just like using the distributive property. So you're going to multiply 4 by every number in the matrix. And that's going to give you the same size matrix you start with. So we're going to have 12, -8, 0, 12, 4, 24. Now we can also reverse this process and we can factor out a scalar. So if you started with my answer matrix, you could factor 4 out of it and leave the 4 on the outside. Okay, here we have a combination of multiplying by a scalar as well as adding matrices. So just think about the order of operations you would use for real numbers and apply the same order of operations. So the first thing I would do is multiply the scalar -3 by the first matrix and write that out. So we have 3, -15, -12, 0. And then we would add the second matrix by adding the elements in like position. And that's going to give us 1, -14, -7, -3. Okay, the next one is very similar to the last one. We have scalar multiplication and we have subtraction, and just go ahead and multiply through by the scalar first. And if you want to multiply by -4 and change this to plus -4 instead of minus, you're welcome to do that, and then you'll just be left with adding at the end. So we're going to end up with 8, 1, 12, 15, -1, 3, plus -24, -12, -4, 8, -32, -12. Now we add those together. So we have -16, -11, 8, 23, -33, -9. Okay, so that takes us through addition and subtraction and scalar multiplication, and sometimes you'll have those operations embedded in a problem like this. Let's solve this matrix equation for x and y. So notice there's a 2 on the outside, and then we have this sum in parentheses, so we would be distributing the 2. And when we add the matrices, we would add elements in like position. So if you break it down, it really just boils down to, if you want to find x, you're going to have 2 times, find the x, and find all the elements in that position. So 2 times the quantity, 2x plus -1, equals 10. See, we just used the 2 and then everything that was in that same position in the matrix, first row, first column. We could divide both sides of the equation by 2, so 2x minus 1 equals 5, add 1 to both sides, and then divide by 2. And then to find the value of y, we're going to do the same kind of thing. Again, use the 2, locate the y, so that's second row, second column, find all the elements in that same position, and then we can set up the equation. 2 times the quantity, the opposite of y plus 5, equals 14. Divide both sides by 2, subtract 5, and divide by -1. And now we know the values of x and y. Okay, the next thing we do is called matrix multiplication. It's significantly more intricate than addition and subtraction, and I'm going to justify it with an example about concession stand sales. So imagine that concession stands were open. Ooh, imagine that you could actually be a spectator at a sport. That's kind of way back in history. And imagine that you could go to the concession stand and buy something. Suppose that they were open on Saturday and Sunday, and they kept track of their sales of popcorn, small, medium, and large, in a matrix. So we have small, medium, large, and this is the number of popcorns they sold on Saturday. 4 small, 5 medium, 6 large. And on Sunday they sold 3 small, 6 medium, and 2 large. So we just arrange the numbers into a matrix, a rectangular arrangement of numbers. This matrix happens to have 2 rows and 3 columns, so it's 2 by 3. Now I'm going to make another matrix which represents the price for small, medium, and large popcorn. And I'm going to do it like this. We have $1 for small, $2 for medium, and $3 for large. Okay. Now, that is a 3 by 1 matrix, 3 rows, 1 column. Suppose I'm interested in finding out how much money they made for popcorn on Saturday and how much money they made for popcorn on Sunday. Well, what I need to do is multiply the number of small popcorns by the price, and then add the product of the number of medium popcorns times the price, and add the product of the number of large popcorns times the price. So we have a sum of 3 products, 4 times 1 plus 5 times 2 plus 6 times 3, and that gives me the total amount of money made on Saturday. So that would be 4 plus 10 plus 18, and that, if I can add, is $32. $32 made on Saturday. We can do the same thing for Sunday. The number of small times the price of a small, plus the number of medium times the price of a medium, times the number of large times the price of a large. 3 times 1 plus 6 times 2 plus 2 times 3. And that, I believe, is $21. So we just have a matrix which represents the total dollar sales on Saturday and the total dollar sales on Sunday. And what we have done here is we have gone across a row and down a column, and we have taken the elements and multiplied and then added each product. And then we went across the next row and down the same column. Imagine you had more rows to go across in the first one and more columns to go down in the second one, then you would have more elements in your answer. So the matrix multiplication process is go across the first matrix and down the second matrix, and do that with every combination of every row and every column. So now let's put that into a little bit of a general terms here. To multiply, let me go back for a second. Notice that the number of columns of the first matrix, 3, matched the number of rows of the second matrix, 3, because you have to have them line up or it's not going to work. We had to have 3 numbers across and 3 numbers down so that they would match up. Okay, you couldn't sell small, medium, and large and only have prices for small and medium and no price for large. It just wouldn't match up. Therefore, if you're going to multiply matrices A and B, the number of columns of matrix A has to be the same as the number of rows of matrix B. Those inside 2 numbers must be the same. The product, when you multiply A times B, you can just call AB. You don't need a symbol in between. And then to generalize, I'm going to use this 2 by 2 example where matrix A has elements A, B, C, and D, and matrix B has elements E, F, G, and H. And it is very common for people to kind of get tripped up on this process and maybe just not quite get it at first. So if that happens to you, please don't be overly concerned. Just ask for help and we'll just keep trying till you get it. So notice that matrix A is 2 by 2 and matrix B is 2 by 2. So the inside numbers do match. And also, the outside numbers are going to tell you the dimensions of your answer. So 2 by 2 happens to be the answer. If we look back at the example, the outside numbers 2 by 1, those were the dimensions of the answer, 2 by 1. Okay, so going back here, what we're going to do is we know we're going to get a 2 by 2 matrix, and we're going to take the numbers in the first row of the first matrix and the numbers in the first column of the second matrix, and we multiply like elements together. So we have A times E plus B times G. First elements multiplied, second elements multiplied. Okay, that number would be the first number in your answer. Now what we're going to do is take the first row of the first matrix and the second column of the second matrix and go across and down. So we have A times F plus B times H. And that number is going to be the second column, first row. Okay, now we're going to move on down to the second row of the first matrix, first column of the second matrix. So across and down. So we're going to multiply C times E plus D times G. And then for the fourth combination, second row, second column, across and down, C times F plus D times H. All right, that's the process. Now this video is getting kind of long, so I'm going to break this up into 2 videos, and in the next one we're going to work through some examples of multiplying matrices, because this is something we really do need practice with.